Welcome, ladies and gentlemen, to the fourth pre-lab webinar. This will cover recrystallization and will deal with the experiment that we're doing Monday, September 25th. In this presentation, we will discuss some announcements, go over laboratory record keeping, and we will discuss purifying solid compounds, which includes recrystallization schemes, solubility and recovery, impurity classification, choosing solvents, and steps and results that you should see with the experiment that you'll be doing Monday. Your extra credit assignment, rather your first extra credit assignment, will be due at 3:05 p.m. on Monday. A second assignment will become available to you near that same time on Monday and is on iLearn already. You just won't see it until Monday at 3. The assignment there will deal with some general chemistry calculations pertinent to the items we'll discuss today and some of experiments we'll be covering before your next quiz. With regard to lab reports, there's a Dropbox on iLearn for each lab report. Template forms will generally be accessible for each experiment under the appropriate experiment tab on iLearn. And I did check the dates because some of you were asking. Dr. Krause has set the first 2 reports. The others he has not finished setting up yet, but the first 2 are set. And your first report on melting point will be due October 2nd at 11:59 p.m. Central Standard Time. The second report on recrystallization will be due October 9th at that same time. Dr. Krause is the one that sets all of those due dates. I have nothing to do with them, and I don't normally know when they are, so you will have to look on there. But he generally only opens up a couple at a time. And as far as exceptions to those deadlines, if you turn in a late report, there is usually a point deduction for that. However, exceptions are made if you're making up the lab, and in that case you would need to work with Dr. Krause on that regardless, because he has to go in and set the deadline for you. If you turn in a report, you cannot make up the experiment. So it's important that if you are making up an experiment that you only do so, or realize that you can only do so if you haven't submitted a report for it. So if you're dissatisfied for some reason with your data or your product and you feel a need to redo it. And I will remind you that typically redoing products does not help students' grades, and so it's generally not worth all the time and effort to go back and redo it again. But if you do choose to do that, you cannot turn in the report, because if you did, you won't be able to make it up again. With regard to pre-labs and dailies, I wanted to touch on this issue because it seems that there are several people in the class that appear to be struggling with understanding the requirements for these items and turning them in on time and that sort of thing. And that's not a good start to the term, because we normally don't have as many of these kinds of problems with this, and I'm not understanding exactly where that error seems to come from. I think it's from not reading things carefully enough, but the information that you need is contained within pages 6 through 10 of the Laboratory Exercises Manual for Organic Chemistry, 11th edition, which is the current edition, and that is the one published by Dr. Krause. Item 6 covers the pre-lab entries in the notebooks and the format for those. Those are the things you're turning in before lab. You must turn in one to work in the lab. If you don't, then you cannot be allowed to work that day, and we'll have to make up the experiment some other time, if possible. And it may be that we reach a point where that's not possible, and so then the consequences might be worse than that. Specific things that aren't part of the general format that need to go in each one are generally published in the manual on the experiment write-up. And they are labeled pre-labs in the section in that manual. So you can normally tell what part of it is meant for you to read on that. As far as your daily entries go, there is a general format for those described in item 7 of that list through pages 6 through 10. And then item 8 discusses post-lab entries, which I'll detail a little bit later. And then the final 2 pages discuss appropriate lab report skills and how to write the discussions so that you're not counted off points for not following proper format and that kind of thing. Post-lab entries, or summaries, as I have been calling them. There is a little bit of a name ambiguity because different people use different names, but in your manual it's called a post-lab entry. Those are things that, those are the specific items that I told you need to leave a page in between each experiment for. So you can put it in there, because sometimes you get spectra back that you have to wait on, and that page is where those things are attached. So anything like a TLC plate or a spectra or a drawing, or if you're hand drawing a graph or something like that that you're doing for your post-lab entry, that goes on the same page as the post-lab entry. These things will vary depending on the type of experiment that is entailed, and it's hard to say exactly what all you should be putting, but in my own view, the best way I can show you is to say that you should read through the criteria that are in the lab manual and make sure you're following that general criteria, but also during each pre-lab webinar I'll try to include a very, very brief note on the items that I might expect to look for because of the way it might synthesize the data better, or kind of give you a main idea of a working framework for what that kind of experiment might be summarized like. So for the melting point experiment, what I think you should probably do with your summary is make a hand-drawn graph of the starting points and the ending points, like some of you did in the lab and that you did on your lab report. It doesn't have to be one with a line, you can just make a scatter plot. And you should discuss or interpret those graphical results and relate it back to the meanings of the data in the experiment. That would be a sufficient summary for the Thiele tube melting point, mixed melting point experiment. And you could maybe explain the purpose of mixed melting point and talk about what some of the special points on that graph mean, or something like that. And that could be a good summary. Recrystallization, again, there's not many graphs with this, but you could do a demonstration of your calculation work showing how you go through the process of recrystallization, some of the perhaps solubility differences variable to temperature, maybe even include like a small flow chart, kind of like the one that we'll see in this presentation where it talks about the process, and you could tailor it to the specific compounds perhaps that you're using in this process. And then you could discuss all of that and maybe give kind of a brief relation to the particular experiment and substances and kind of explain how it all works out in very, very brief context. What I will say about these post-lab summaries is that they do not need to be epic in nature. Brevity is the soul of wit, and therefore it's you know, oftentimes when I was in medical school and had to take medical histories from patients and you're writing things in the chart, one thing you learn is not to write everything down in full sentences, because if you do that you'll take forever and write forever on the things that they're telling you. And most doctors actually gripe at you if you do it. They want bullet points because they want to get to the facts they need to know to make the decisions they need to make quickly and effectively. And so the same goes for these kinds of documents here. While you want to have good grammar and that sort of thing, you also want to be to the point. And you want to tell good information quickly and learn to be efficient about it. So bullet points, like the ones on this slide, are not a bad idea. As long as they're in, some sort of short, meaningful sentence that makes sense with what you're talking about, they could be acceptable for a summarization if you're trying to point out something on a diagram. And you'll just have to be kind of smart about how you organize your information, and everybody will do things differently. I mean, some people like to write in paragraphs and sentences. In my view, from previous experience with journalism and other things in life, I believe that a good paragraph can be 3 sentences for me, and they can be 3 short sentences. Some people will do the old English standard and say 5 sentences. I don't really care. I just want good, solid thought and good, solid conclusions that are effective and meaningful. Alright, now on to business, purifying solid compounds. So recrystallization is something that you only do for solid compounds. You don't do it for anything like a liquid or a gas, because those have usually a distillation process that you use to purify them, or sometimes a chromatography process. It just depends on the situation and what you're trying to do. But either way, when it comes to recrystallizing, you have your solute, which is the thing you want to purify, but can also be impurities if they're soluble. So it's really the material you're starting with. And then your solvent, which can be a single solvent or it could be a mixed solvent with different components. Now, if a solute is soluble or a solute is insoluble, it makes a difference how you're viewing this component. So typically, to recrystallize something, you want that to be soluble. You just don't want it to be so soluble that it does it at any temperature. You typically want something that dissolves as you heat it up, and that when it cools back down will re-solidify. But you also want the soluble impurities to stay in solution at any temperature. So soluble solutes can go a long way with recrystallization, and there's two different variants on that. Then you have insoluble solutes, and those are things that you typically want to be impurities. It's a great and easy separation if something you're trying to separate won't dissolve in the solvent that your compound you want to purify will, because then you can just easily filter the insoluble away and then recrystallize the compound you want to purify. And then as to impurities themselves, like we just said, they can be soluble or insoluble. You can gravity filter the insoluble. When it is soluble, you also have to take the extra step of looking at the color change that may be in solution because of the impurity. If it's a colorless event, then you don't have to take any steps with that. If there is a color discoloration or some kind of foreign color because of an impurity, adding activated or what they call decolorizing charcoal in our lab can actually help remove some of that a little bit better. We'll kind of walk through each of those things on that schematic a little bit more detailed now. And we'll start with solvent selection, because that's the most important part of doing a recrystallization. So if you have varied solubility with temperature, that is really the governing factor in picking a solvent, because you want your solvent to dissolve your material you want to purify at a high temperature but allow it to recrystallize at a lower temperature. So in this case, we've chosen benzoic acid as a substrate, and we've used water as the solvent for this recrystallization. And this is actually the classical and traditional method for recrystallizing benzoic acid. So when you heat it up, the solubility of benzoic acid increases significantly compared to the solubility it has at a lower temperature. That allows you to trap the soluble impurities and keep those in solution, and to recover your benzoic acid. It also allows you to filter out any insoluble impurities while it's hot. Now, to make matters a little bit more perspective placed for you, what I would suggest is that you take a look here at the items being asked, because you should be in the habit of, whenever you're given information like this, being able to look at it and determine how you can relate that in an equation to something useful you can measure in the lab. And one of those things that's useful is deciding about how much solvent you need to use in order to just get things into solution, but not overdo it on the solvent, because it will take longer to get things back if you over dilute. Because rate laws on solubility apply just like rate laws for reactions. If you concentrate the solvent, you're going to make it really easy to go into solution, just as much as if you increase temperature or some other thing like leaving it there longer to equilibrate, any of those things really. So the first thing is, can you determine how much of a compound should dissolve? And to do that, you have to know the solubility and you have to know the temperature at which your system is going to be. And if you know those two things, then you can calculate it if you know the mass or the volume that you want to have. And then you have to be able to determine how much you can recover if the temperature changes with those constant settings from the first part. And then after that's all over with, you should be able to calculate your percent recovery from doing a recrystallization. And that is important because it tracks the efficiency of what you're doing. If a process isn't going to give me, 70 to 90% of my material back, I'm going to try to find a process that's at least going to give me more towards that 90-95%. Sometimes you can't find one, and it is the case that a normal process for some things could be that we'll only get 40% back when we purify it. And that just depends on the process and what methods are actually available to do it successfully. Impurities, like we had mentioned, can be insoluble and soluble. If they're insoluble, we can easily remove those just doing gravity filtration while we have warm solvent still, and the solute that we want to recrystallize is still in solution and can flow through the gravity filter paper. When it's a soluble impurity, it's going to go through that gravity filter, in which case we rely on those staying in solution at every temperature, not just the temperature that we're going to bring our precipitate back to, or that at which our precipitate is dissolved. Here I mentioned, the cold vacuum filtration removes this, and that is true, but that's not the main reason we do the cold vacuum filtration. Exactly, it's got more to do with another item we'll discuss. Now, as to picking your solvent, again, from what we've observed, there are some rules you want to follow. First, the dissolving of the solute happens when it's hot, and that's for the compound that we want to purify, but not when it's cold, because we want it to come back out again so we can recover it. However, the impurities we want to stay dissolved when it's cold, or we don't want them to dissolve at all. We also don't want our solvent to decompose when it's heated, and we prefer that the boiling point be pretty low so that we can easily evaporate it. One of the easiest and quickest ways to do this is with a rotovap. We don't actually use rotovaps in our organic chemistry lab because it's more of a research piece of equipment. But it can tremendously impact the speed at which you can recover solvents. We can also distill and use columns in order to evaporate and condense items. We can also do open kind of beaker evaporations, doing them in the hood or something. And then if it's something like water or just pure ethanol, oftentimes you can, if you have a small amount, you could do it on a steam bath in a well-ventilated area and it wouldn't be a hazard. But it just depends on the substance and what you're working with. Now, as far as the steps and kind of demonstrating them, these pictures were taken a long time ago, and I want to point out while I'm going through them that there is a difference in the way we were doing things then and the way we are now. So in this particular lab, we were using hot plates to heat the glassware and to do all of this, and this is how it was when I was a student doing this laboratory for the first time. And the hard part, I think, was keeping everything warm, because on the steam bath it constantly produces a little bit of warm water vapor. So if you set up your gravity filter right, you can actually keep everything pretty warm, and the moisture kind of helps insulate the warmth so it doesn't get cold too fast. Whereas this one, there's not that kind of water vapor in the air. It's very dry because it's more open, so there's not as much heat retention in this kind of a setup. But the first step, of course, is getting everything into solution. So when you figure out your minimal amount of solvent to add to the amount of mass that you're using, and then, you know, to heat it up and get it all into solution, you then look at the color. Sometimes you'll have little color impurities that can be present. So if there are color impurities, then you add some charcoal to that. If there's no color, then you don't necessarily need the charcoal, because it only helps with some color. Sometimes compounds have a color. If it's the natural color of a compound, you're probably not going to remove that with charcoal, and you wouldn't want to in that case. The second step, of course, is to get rid of your insoluble impurities. And so to do that, you have to set up a gravity filtration system. And you have to do this while everything's warm. Now, the first step in any gravity filtration is getting the right filter paper for the job. And there's different kinds of filter paper. There's coarse filter paper and fine filter paper. There are different sizes of diameters of filter paper. And generally, they are measured by their diameter in centimeters. In some cases, in millimeters. It depends, as I said, on the particular situation. For our microreel scale kits, oftentimes we use a Hirsch funnel because it is smaller and we make less material. And so for those purposes, it tends to be fine. However, the filter paper that fits in those funnels is about 1.5 centimeters in diameter, so it's fairly small, and we have to custom make them from other filters in most cases. Most of you have funnels big enough to where you can use a good 7.5 to 9 centimeter filter paper, sometimes 13. It just depends on the size of your funnel, really. You don't want your filter paper to be so thick that it encumbers flow, because it will cool down when your solution is going to cool down when you put it into that filter, even if you have it over a steam bath. There's going to be a pretty decent temperature change. So you really want the flow to be not too encumbering, because you don't want your fluid to sit there a long time and possibly start having precipitation of compound that you want carried through the filter so that it can come out cleaner. We only want to trap the charcoal and the insoluble impurities in the gravity filter. So that's kind of the basic of the filter and kind of how to pick the right paper. And again, it depends on the compound. If it's a thick liquid, You don't want a fine filter, you want a coarse filter, or you'll be there forever and it may never go through the funnel. I have had that experience. It's not fun. The second thing to take into consideration, aside from picking the right filter, is how you fold the filter paper. Now, your book shows you 2 different ways, and really there are 2 different ways to do it. There really aren't many variations to this. The most common way is to make just a very standard quarter fold and open up one flap and leave the other on the side, and it makes a cone that you can filter things through. Most of the time when I'm doing a project, that is the method that I use. I normally don't do the fluting, mainly because I'm impatient and don't like to spend that long making filter papers, but also because it doesn't always necessarily provide an advantage depending on the situation, and it can be a needless task if it's not going to give you the advantage you need. In your case, it's probably advantageous because you don't know what impurities you have. Sometimes they put inert materials like silica or something in the mixture so that you have some insolubles to get out through this filter. And so, because you want to maximize your flow and keep things warm, you really want to maximize as much as you can your surface area for grabbing, kind of, I don't want to say grappling, but grabbing onto the materials. And to do that, you can increase your surface area to volume ratio by fluting your filter paper like this, because it gives it little ridges to kind of attach to as opposed to just plain old material. And like I said, sometimes plain material is fine. It depends on the situation. Most of my stuff, we didn't necessarily have to do the fluting, but if you like to do it, you know, some people do it all the time and others don't. It just depends on preference and what you're doing. But to do it, it's pretty simple. You make that quarter fold and you start folding it into little bitty pizza slices, basically, and you just kind of do that as many as it can do, going in kind of a systematic manner, and then you fold it back open again and you have this fanned out looking conical fluted shape, and that's your filter paper to use. So pretty easy. These steps go as the following: 1, 2, 3, 4, 5, 6. That's the way you want to read those pictures. As far as using it, like I had mentioned, in this setup you had to keep things on the heating plate as much as you could, and you still kept it on the heating plate even when you filtered it, and you had to pour it through the filter. On the steam baths, you can set multiple things on it because you have rings of different sizes, and it keeps it warm on there, and as long as you're keeping it with the steam and keeping things warm, it'll work pretty well for you. You do want to get as close to your heat source as you can with your funnel, and most of you will have these cut-off funnels. Actually, believe it or not, a funnel stem actually makes working with a funnel harder than not having a stem. It's easier to take advantage of the conical shape and let it drain into a larger beaker than it is to try to position some of those long-necked funnels into like a jar or something, because oftentimes you'll get it kinked with your clamp and you get too much distance between the heat source and you can't insulate this process as well with the water vapor or with the heat that you have, and so it can be cumbersome, and also it's a little bit more unstable. I've generally seen funnels break more because they had the stems and break less because they didn't. So that's just kind of the general way that funnels tend to go. Regardless, you will have to be a little bit patient. It depends on the fluid. Most of you will work with sort of semi-aqueous fluids or fluids that have some water content with these experiments we're doing, so it'll be pretty easy to filter through. Sometimes if you're working on something like a petroleum, or if it's like a, you know, more of an oil-based system, it can take longer. Once you do gravity filter it, you take the filtrate from that filtration and you place it into an ice bath. Now we'll be using a plain ice bath, which will only bring you to 0 degrees Celsius, and that's it. You can't get colder than that. Sometimes we have a need to cool things even more than that, and to keep things around 1 to 3 degrees Celsius at most while we're actively heating the system. It depends on what you're doing, but in those cases you can modify these baths. And your Making Connections text talks a little bit about how to design different kinds of cooling baths for your experiments. There's CO2, solid dry ice. Basically, you can use dry ice and acetone, liquid nitrogen acetone slushes, sodium chloride and ice water, calcium chloride and ice water. There's all kinds of different ones you can employ. It just depends on your needs. But regardless, you have to be patient and you just have to wait. So most of you, when you're working with a solid product, and we will make several solid products during our time together this term, and also especially next term, one thing to keep in mind is that generally you don't take a melting point until the week following the retrieval of your crystals, because you want to check the impurity and or rather you want to check the purity and check and see if there's impurities in it by doing your melting points, and you're going to have impurities if your solvent's not all dry. So typically what I always recommend, and what you could even do now if you were in a boat where you needed to maybe take a melting point for some reason, which I don't think we are, because we didn't do a melting, we did all those melting point experiments in lab and made graphs with them and whatnot. But if we had a product per se, while you're waiting for it to cool down and precipitate, you could be taking those melting points on a melt-temp apparatus or an SRS Digimelt apparatus or whatever it was we were using, and you could utilize that time while you're waiting. And that would be a decent time during most of our experiments to look at doing something like that, because you just have to be patient for this to happen. I will not stress enough the importance of being patient when it comes to recrystallization. Most of you want to get done as quickly as you can with this, and what I can tell you is that if you do that, you will more than likely not get the result you want. Crystals, when they recrystallize, you'll always hear people tell you that you want them to be long and needle-like, kind of like this shape here that I'm going to draw in this purple ink, I think it is. And for something like benzoic acid, that shape I just drew up here on the top of the screen is probably pretty normal and ideal, because it makes long needle-like crystals. But sometimes crystals don't look like that. Sometimes they're short needles. Sometimes they tend to be more diamond-like or more square-like looking. It just depends on the material, and it depends on your technique as well. So one of the things you'll often hear is that if you're getting a powder instead of crystals, you've probably got more impurities in that sample. That could be true, but it could also be normal for that compound. It depends on what you're working with. And most of the time that happens, people were impatient and tried doing a bunch of things to their solution to make it crystallize earlier, or sooner than it should have, or they got water in their solvent or something and it caused some to come out, and then when one came out, everything came out and it trapped impurities possibly with it. So you want it to form crystals on its own and be patient. Now, there are some things I haven't talked about in here that I will put on another slide at the end that discuss methods of getting things to recrystallize that have difficulty doing so, because there are some times that you need to know skills like that. But for this particular recrystallization, the main thing you need is patience and following the directions. As far as the final step in a recrystallization, that will be your vacuum filtration. So when you do a vacuum filtration, you want your solvent to be cooled down. So you're pouring it from that ice bath that it was sitting in. Your filter paper goes in your Buchner funnel. It goes in flat. And it needs to fit right in the funnel. There's different diameters of funnel. There's different diameters of filter papers. It all needs to match up. These hoses are vacuum tubing. So remember that the vacuum tubing is different from regular water tubing, and you need to use vacuum tubing whenever you're going to use the vacuum filter, because these hoses can withstand the hoses can actually withstand quite a bit of vacuum pressure, but the maximum amount of pressure that you can give as negative pressure in this system using the aspirators like we do in our lab will be about 10 to 15 torricellis of pressure. So you're not going to get much more than that on a water faucet, but with a properly regulated commercial pump, you can get much more than that. And, you know, the more vacuum you pull, the faster the flow tends to be. But that can also be a bad thing. You don't want to overtax the system or pull on the filter paper too fast while it's wet and cause it to tear and pull things. You know, you have to treat the system with respect. The other thing I'll point out is you want to make sure that when you hook up your vacuum filters that you're employing the use of your check valve. The check valve is a one-way valve system designed to ensure that the flow of the vacuum goes toward the sink and not back towards the funnel. What happens sometimes on these water aspirators is that the way the water flows doesn't always sync up with your vacuum, or you get, you know, some kind of a non-steady state sort of flow going on in this tube, and what happens is it will back flush and water will come into the filter and sometimes slosh into the material if there's enough stuff in here. So you have to be a little bit careful about that, and one way we avoid that is with the check valve. It's also the case that if too much fills up in here, you'll actually suck mass out from the filtrate into the system. So you don't want more, you don't want excess fillage in this, well, not excess, you don't want any excess filling in this vacuum flask. Another way you might see this hooked up in a laboratory, and that actually is safer even than this, is what we call a secondary containment flask. And so, or some people will call it like a check flask, or a trap is another, a trap is a more common term, making a trap, they call it. So, to do that, you take another vacuum flask, you hook the vacuum hose with the check valve onto the nub right here for the check with the outlet for the vacuum, and then on top you have one of these silicone stoppers, but it typically has a piece of glass tubing in there that's pretty sturdy, and you hook another vacuum hose on the top of that, and so the top part feeds from the flask that you started in, And you could even have a check valve there if you wanted to ensure no backflow from the trap. And then you could have a hose hooked into the top, and then you'd have another hose attached to the vacuum outlet on the trap, then one to the check valve, and then to the aspirator or to the vacuum pump. Most of the time you employ a trap whenever you're using one of those commercial vacuum pumps, because you don't want to get fluid in your pump. That can damage the pump over time. They're not really made for that, and it depends on the situation. But also, you might use a trap with an aspirator if you were working with a solvent system that you did not want to accidentally get into the water supply. So it just depends on the situation. A good rule of thumb for you all, because you are working with things that we don't necessarily want in the water supply, would be that whenever you're getting about 3/4 full, you turn off the vacuum and you empty the vacuum flask into the waste before continuing to wash or anything else that you're doing to your precipitate. The other piece of information on that is, when you're filtering, you're going to have solids that stay in the beaker and kind of get stuck on the sides, so you have to work with your spatula and you have to get as much of that out as you can. You don't usually want to use solvent to wash it out, because you're going to put more contact with solvent there. And remember that it isn't just temperature that makes things be soluble, it's the concentration of solvent and the amount of time that they sit in the solvent. So all of those factors apply. Therefore, we want cool temperatures, we want minimal contact time, and we want low concentration of solvent as much as we can when we're trying to do the process of getting our precipitate out of solution. When you do finally get as much of it as you can out of the beaker, you can take some chilled solvent and you can wash any remaining crystals into the flask with a minimal amount. You can also do one little rinse or two with some cold solvent very minimally on the top of the flask, and that will pull through any impurities that didn't go through automatically. But you just don't want to put a bunch in, because then you're going to possibly take some of the compound that you wanted to get out with you into the filtrate, and it will likely not come out again. So that is something you have to keep in mind when you're recrystallizing. You've got to be patient and be careful. Now, at the end of the process, what you hope to have are these, again, needle-like looking crystals that have formed on their own. And this is an evaporating dish, and it's one of the main purposes of an evaporating dish. It's made for evaporating solvent. So it has nice surface area. When you put your filter paper down on here from your Buchner funnel, you can kind of spread out the material with your micro spatula, and if you leave something like that in your drawer for a week, it'll dry most of the time. And when it does dry, you can take a melting point of it, and it won't sweat or cause impurities like we talked about in the last webinar. So this kind of builds on the melting point idea, because this is the thing you have to do in order to get good sharp melting points with most of your compounds you make. And the final thing that I wanted to talk with you about today are some additional precipitation methods that you may encounter in the lab manual, and that you may have to employ in future reactions when we work with more complicated products that can be difficult to recrystallize in solvent on their own. The easiest example I can pick would be the Grignard reaction. a lot of times the alcohol that you make from that process kind of forms as a goopy mixture, and you have to get the impurities to dissolve in solvent of your choosing, just like we do with any of our other solid compounds. But it can be difficult also sometimes to get that material to seed on its own. So one of the things that you can do whenever you have, and we'll talk about what I mean by seed as well, but one of the things that you can do is what we call trituration. I think some people also say trituration, but I call it trituration. And what we mean by that word, and it is spelled exactly like I've spelled it on the slide, despite the fact your word processors and things will tell you that it's wrong or something, because nobody's really used to this word except a chemist. But what it means is that you're taking something like a beaker, whatever vessel it is that you're using to contain your compound in your solvent. We'll say I have a beaker. And it's got some little graduation marks on here. And we'll also put in some solvent. We'll make it green. And then we'll add to that some particles to show that we have something we want to get out, but it's not necessarily forming crystals for us. And that could be for either of these cases here that are on this slide, but we'll just kind of go with this as a model. And what I do when I want to triturate something is I take a glass stirring rod and I make a little bit of a scratching zigzag type motion on the bottom of the beaker. What I do by doing that is I'm looking to make a very, very small, you might even call it beyond microscopic, but it probably is actually a microscopic injury to the glass, but I'll say nanometric because I think it's more on that level when you're really working with something like this. You have a groove that you're kind of creating by doing it, and what these grooves do is they act as kind of surface points for a couple of those molecules or atoms or whatever it is. It'd be molecules in this case, but whatever particles you're trying to get to go into some sort of a formation for you, it acts as a little bit of a well so that they can kind of come in and orient physically to one another. And so what's happening is that orientation, once they kind of develop an orientation, they line up, and that lining up can be what we call a nidus or a seeding effect for crystal formation. And I call it specifically in this presentation the crystal cascade. And I call it a cascade because it's very much a reaction that occurs. It's not a chemical reaction in the sense that you're actually making a new compound, but it is a physical reaction, and it is a chain reaction of events that propagates into a result. And so what's happening is, as one crystal or two picks up and orients, they all kind of get into a position, and if one crystal forms, then all of the other molecules can line up and make themselves into a lattice. And that reaction happens throughout the beaker, and you develop your crystals. just by doing that simple triturating / scratching motion. So that's one method if they're not coming out on their own, and it's been a long time beyond what you would expect. That's one method. The other method is if you already have some of your purified compound, and this works pretty well too. What you can do, if you take just one crystal that you can visibly pick up or see with a stirring rod or some kind of a micro spatula, really anything, you just need a little bit. Just one is enough in many cases. What you would do is you take that crystal and you drop it into the solution. And what happens is that crystal that is of the pure compound acts as a nidus or a lattice point for the others, and they can orient to that crystal formation, and then they will engage in a cascade response that forms a crystal lattice. And you can get those out of solution. And I apologize that I can't really draw a better crystal lattice, but it's difficult to draw with the mouse, and there's not really a good little bitty crystal I can make with it. Anyway, but that's the idea. And it's effective, but you normally don't want to have to do it if you can avoid it. It's better to not do these things, because typically what happens whenever you try to do something like this, you end up introducing an impurity, because those stirring rods aren't always very clean. The beaker may not be perfectly clean, and you're scratching things. And sometimes, even though your soluble impurities are supposed to remain in solution, if you engage in this process too quickly, you can actually cause a lattice to form around impurities, and it could trap little bitty volumes of it and be impure. So you have to be careful about rushing the recrystallization process. It's meant to be kind of a slow, well-paced, temperature-controlled process. But sometimes you do have to help things a little bit. And when you do, you just want to do so conservatively and carefully, and you'll generally get a good result. That's the basis of all recrystallization. It doesn't matter what you're doing. If you're making a solid compound and you want to purify it, that's pretty much the only way that I can think of that you can do it the best, is to recrystallize it. It's like a common step, and we'll do it a lot, and you'll get to where you do it automatically, even though it'll tell you what to use to do it, but you know you'll have to, more than likely, and that you have to let it dry before you can get your melting points for your reports and things. But you'll use this skill from here on out. It's an important skill to learn. I don't care if you're going to be an engineer, or if you're going to just be a chemist, or if you're not really planning on doing much at all with chemistry, or if you're going to work in some other kind of laboratory like a pharmacy one or something like that. You'll probably use some kind of method like this to purify compounds, because I'm pretty sure even in the industry they probably have large vats that they recrystallize solid substances in. So these principles will apply even there, because the general principles of it don't change much. The math we might use to describe it may, or the size of the process may change, or even the materials, but in general these methods are what you have to work with when you're working with a solid. And that's true even of inorganic substances, not just, in inorganic labs they precipitate things out of solution all the time too, because they make compounds that are solid sometimes. And this is just a general solid recovery method. If you want to purify something, that's what you have to do. But that's all we have, and you'll want to work with that. Think on it, make sure you do your pre-lab correctly, make sure you're ready to go on Monday, and we'll see you then.